Hi class, we are now on 14.4. This is, we have one more section to go. At least I believe we are. In the previous lessons, we introduced redox reactions. In this lesson, we're going to show how to balance these equations. As with other balanced equations, this means that the total number and type of atom must equal on both sides of the equation. When describing redox reactions, we must also balance the charge as well. Stated differently, the same number of electrons lost in the oxidation will be gained in the reduction. For example, this unbalanced equation shows the reaction of calcium metal with aqueous chromium 3. In this reaction, elemental calcium is oxidized to calcium with the 2 plus charge, while chromium with the 3 plus charge is reduced to elemental chromium. How do we go about balancing this? There are two approaches. We can write it as a complete reaction and balance the total charge, or we can separate it into half reactions and balance each of these. We'll look at both approaches. Okay, I didn't realize I didn't take that off. I always try to take that stuff off. Okay, so here's the first approach. It's not going to probably make sense. Don't panic. Notice that in this equation, the number, make sure it's not, yep, I didn't take any of these things off of it. I hate that they do that vanishing stuff. Okay, so notice that in this equation, the number and type of the atoms are the same on both sides, but the charge is not. To balance the charges, we must add a 2 in front of the chromium 3 plus and a 3 in front of the calcium 2 plus. Now the charge is balanced. There is a total of plus 6 on both sides, but the atoms are not balanced. To balance the number of atoms, we add coefficients to the elemental forms, 3 calcium atoms and 2 chromium atoms. Now the total charge and the number of atoms are balanced. I don't like this. I didn't learn how to do this. We're going to look at approach 2, which okay. I didn't realize I didn't remove any of this stuff. I want to put it all out there just so we can talk about it. Okay, so approach 2 is the way that I know how to do it, and that's what we're going to do for this section. So approach 2 is another way to tackle this problem is to make sure that the same number of electrons are released in the oxidation and acquired in the reduction. We begin by writing the 2 unbalanced reactions. So you know what, might as well take advantage of it with it here. So we write both reactions out, okay? The oxidation releases 2 electrons, but the reduction requires 3. In order to balance an oxidation-reduction reaction, the electrons lost in the oxidation must equal the electrons gained in the reduction. To make the electrons equal, we multiply each species in the oxidation factor by a factor of 3, and each species in the reduction by a factor of 2. Now 6 electrons are lost in the oxidation, and 6 electrons are gained in the reduction. Finally, we add the oxidation-reduction reactions, half reactions, together to obtain the net ionic equation. Because the same number of electrons are present on both the left and right sides of the equation, we can cancel them out, leaving the correctly balanced net ionic equation of 3 calciums that are solids plus 2 chromium 3 plus charges in aqueous solution results in 3 calcium ions and 2 chromium atoms that are solid. Okay, so the number and the type of atoms and the total charges, this balances now. So this is the way that I was taught how to do it. I can't just, if we go backwards, I can't just look at something and wing this and decide what is what. It doesn't make sense to me that way. I actually have to work everything out in order to see it. So let's take a look at this problem. Silver metal undergoes a single displacement reaction with platinum 2 nitrate to form silver nitrate and elemental platinum. Write a balanced net ionic equation for this single displacement reaction. Let's solve this problem using both of the methods we discussed. First, let's do it by balancing the atoms and the charge in the net ionic equation. We write the unbalanced equation like this, and I think I didn't replace these either. Okay. So let's go back. Nitrate is a spectator ion, so it doesn't need to be included in the net ionic equation. First, we balance the charge by adding a coefficient 2 in front of the silver ion. We then balance the number and type of atoms by adding a 2 in front of the elemental silver. The number and type of atoms are now the same as well as the charge on both sides. This equation is balanced. But let's look at one more example. So silver metal undergoes a single displacement reaction with platinum to nitrate to form silver nitride. Write a balanced equation. The alternate approach is to balance the electron flow and the oxidation reduction. This is the only way I know how to do it. So we begin by writing the half reactions. So we write the first reaction out, and then we write the reduction out. To balance the electrons in each half reaction, we multiply each species in the oxidation by 2. We then combine the two half reactions. There are 2 electrons on both the reactant and product side, so we cancel them out. This gives us the balanced net ionic equation. So if we plug this in, and then we can cancel out, and we end up with the balanced net ionic equation on it. So these are pretty much the same steps regardless of what the equations look like. These are the steps of how to do it. You figure out what is the oxidation, what is the reduction, get rid of anything that doesn't actually apply to the net ionic equation, and then you can bring down everything once you cancel out that stuff. So now I'm going to show you, it's not moving. Why is it not moving? Okay. So let's do a review here. Number and type of charge. To balance redox reactions, we need the number and type of atoms. Number and type of atoms, the charge. So we have to make sure everything's balanced to the number and the type of atoms. So then in this case, we have these two, and I broke this up. I tried to write as clean as possible to make it understood. So this may look a little messy. I took the first equation, so what we have here is only the first equation. So if you look here, I pulled out the oxidation. So we see we have aluminum, and what's written in black is the original. So I broke it into the ion plus the 3 electrons that come from leaving, resulting in an ion. So now we have bromide 2, which may seem a little confusing at first, but this is an aqueous solution. It is not a gas. So in this case, we take just bromide 2, and if you get confused on what to do, look at the other side. So in this side, it's bromide with a charge. So it's got a negative charge. That means it's taking electrons. It's not at a 0 state. It's taking electrons. So that results in a negative charge. So it's an anion. So if that's the case, then that means that I need to put electrons into it. So that's where this comes in. I have 2 of them. Bromine is a -1 charge, so I need 2 of them. So what you don't see here, because this is imbalanced, is that there's a 2 here. How do I know that? Well, I just got to look over here. So I just plugged in the 2. Then I noticed that in order to get these to balance, this has to be a 6, because these are factors into 6. So in this case, there's 3 and there's 2. So I just crisscross them. That equals 6 electrons. We can cancel that out, and it gives me the net ionic equation on the bottom. So now we do the same for the second equation. And in the second equation, we can see, same thing, I went through the same exact steps. I figured out this one had 2 electrons, the bottom one has 3. So I multiplied the top one by 3. Everything in it, I multiply the bottom equation by 2, and that gives me, and then I cancel out the electrons, and it gives me everything else as a net ionic equation. Now this one's giving you the actual answers very cleanly, but mine shows you how I worked it out. Now this one here is actually, no, it's not. When the following redox equation is balanced, what is the coefficient of silver? So you just got to work it out. So in this case, I removed the nitrate, and I just worked it out completely, the oxidation, the reduction, and you can see that it would be 2 electrons. So, the 2 in front of the silver right here. Okay, so how many electrons are transferred? So in this case, we just look at the previous problem. It is the previous problem, and it's 2 electrons that have been transferred. So it's 2 electrons. Write 2 balanced half reactions to describe this reaction. So again, this is the same reaction, and here it is just written very cleanly compared to all my writing. Write a balanced equation showing the reaction of zinc metal with chromium 2 nitrate. So they've given it, so I actually didn't break it down. By now you should be understanding how to put some balanced reactions together. How many electrons are transferred when zinc metal reacts with chromium 3 nitrate? So this is where I did break it down, and you can see that 6 electrons are being transferred.